Over the course of my studies in theoretical physics, I've traveled across the continent and around the world sampling new ideas and tasting different answers to the questions of how and of why. And still, I find there remains a deep hunger which lives within me, a burning desire to share these great ideas with the people around me. And so, I have assembled a team of some of the greatest, most lucid, most creative minds I've encountered in my travels. And I call them my Titanium Physicists. You're listening to the Titanium Physicists podcast, and I'm Ben Tippett. And now, allez, physique! If we turn our gaze to the depths of outer space, there is one hideous thing which we are sure not to see. Monstrously massive objects, older than the sun and stars, which pull and twist at space-time, and push and play with celestial objects as easily and violently as a child in a bathtub plays with his toys. Oh, but these objects are dark. We can't see them, but we can witness the havoc they wreak as they violently and capriciously toy with the gas and stars which swirl about them. Oh, when they sing, the sweetest and subtlest of songs, they chirp merrily in a hellish language of their own devising. But through which ether do these words carry? There's no air in space, only void. Why, the waves of their song travel as vibrations in space-time itself. But these vibrations are subtle, too rarefied for our human senses to feel. But still, now that we know of these terrible songs, we cannot but crane our ears to listen for them. Even now, our greatest academics and engineers are building great engines housed in tunnels leagues in length, apparati which will let us hear these horrible gibbering songs bubbling from the depths of space, which will inform us about the cold nature of the ancient unknowable. Today, our topic is gravitational waves. And to talk about these deep unknowable objects and the sounds they make, we've invited guests Chad Fifer and Chris Lackey from the HP Lovecraft Literary Podcast at www.hppodcraft.com. The delightful and easy-to-listen-to podcast has a book club format wherein they introduce and summarize and review the stories of H.P. Lovecraft in chronological order. In contrast with the stories, Chad and Chris's discussions are always bright and succinct. Hi, Chad, and hi, Chris.
Thanks for having us on the show. That was a really beautiful intro. I was
amazing.
Writing for a while, and then I realized we were talking science.
Yeah, well, science is creepy in its own way.
Yeah, that's why it's good.
So, Chad and Chris, for you today, I've assembled two of my Titanium Physicists. Arise, Dr. David Sang! Dr. Dave did his undergraduate at UBC and his PhD and master's at Cornell University. He's currently in Caltech working as a postdoc astrophysicist. Now arise, Dr. Jocelyn Reed!
Oh my God.
Dr. Jocelyn did her undergraduate at UBC and her PhD at the University of Wisconsin-Milwaukee. She's currently at the University of Mississippi working on neutron stars. All right, so today we're going to talk about gravitational waves.
What is a gravitational wave?
These are ripples in the fabric of space-time itself, which are these infinitesimally tiny motions coming from space itself, warping in response to the movement of distant objects. And we are actually trying to detect the signature of distant black holes and other crazy compact objects on Earth.
Yeah, so specifically, Albert Einstein, described gravity in terms of a four-dimensional sheet, kind of. It's a surface that has curvature on it. And objects will curve their trajectories according to how this object is curved, kind of like if you roll a marble over a bent-up bed sheet. And also, the mass of objects is what caused this surface to curve. But if you look at what happens when an object accelerates a little bit, it won't cause a big amount of curvature, what it'll do is it'll cause kind of a ripple of curvature that moves outward from the object at the speed of light.
And that ripple of this curvature is gravitational waves. They propagate out just like, an electromagnetic wave, but by rippling space-time rather than the electric and magnetic field.
So light is generated in an electromagnetic field when you accelerate an electron. And the generation of gravitational waves is kind of like the generation of light.
Well, wait a minute. So how do you measure these waves? How do we know they exist? Is it pure theory or speculation, or is there some physical measurement of it?
So Einstein's theory of general relativity predicts that, one of the solutions to his equations is these waves. And we know that it should be generated when you have two massive objects orbiting each other. Now, we have never actually directly measured a gravitational wave. We haven't measured a ripple in space-time, but we can see its effects. For instance, there are these very famous systems where there are two neutron stars orbiting each other. One's called the Hulse-Taylor binary, and the other one is called the double pulsar. And so one of these objects in the Hulse-Taylor binary is a pulsar. A pulsar is a rotating neutron star where it has a beam of radiation coming off of it and acts as a clock as it sort of sweeps around in a circle. That pulse hits us and we can sort of use that as a clock for the neutron star. And as these neutron stars are circling each other, we can see that their orbits are getting closer and closer together as they lose energy to gravitational radiation.
Sorry, gravitational radiation?
Yeah.
Yes, gravitational waves.
Oh, that is gravitational waves are gravitational radiation.
That's right. Sorry. Yeah.
Okay.
These pulsar stars, they're kind of like sirens in space that are spinning at a constant frequency. And so by saying it's a clock, it means that we know that they're not slowing down as they spin. And so we can tell.
Well, they are slowing down. But we know the rate at which they're slowing down.
Yeah.
And they're very regular in their behavior most of the time. They glitch sometimes, but we just don't. We ignore those ones. Don't pay attention to those ones.
So my question is, if I say am Randolph Carter floating in the void of space and I'm near a pulsar, how would this gravitational wave manifest in a physical way that would the images of planets and stars shimmer? Or is it just, I wouldn't even be aware of it?
So you need, say, two pulsars orbiting each other. And say you're hovering in space above the plane of the orbit, so you can see them both going around each other. What you feel is kind of like a tide, of a squeeze and stretch that's pulling your body in a rotating direction.
Yeah.
It's
but
if you're
extremely
in free
subtle.
fall. Yes, this is, well, actually, if you're right above it, it would be a bit more.
Right.
So it's a very subtle thing. It's not something you'd be able to measure particularly easily, and it's very difficult to measure them on Earth, even though we're trying. But what it does, if you're sort of directly above the two objects circling each other, you feel this kind of stretching that's parallel to the plane of the orbit, is this stretching out you're feeling, rotating around, following the orbit of the stars.
Right. So if you had like a little rubber ring, you'd see that rubber ring sort of be squished into an ellipse and then squished into the ellipse the other way.
So Randolph Carter floating out in space would feel his arms pull apart and his head and legs get squished together, and then his head and legs would get stretched apart as his arms got squished together.
I see.
Right. It's kind of an X-shaped pulse. But it deforms things instead of heating them up or getting absorbed by them.
So it'd be like he was in a shifting funhouse mirror, like he would be tall and thin and then squat.
Right, exactly.
Exactly.
One way to imagine it, I guess, is if you imagine two speedboats tied together.
I imagine that all
on the
time.
surface of a lake. And you
Are they doing a jump?
Right. So the individual...
Finally somebody's putting science in speedboat terms, man. I've been waiting for that my whole life.
Okay, rest of the podcast, entirely speedboat analogy.
So, as these speedboats, they're tied together, and they're trying to move in opposite direction. And in the end, what'll happen is they'll end up spinning in a circle as they're tethered together. And just imagine the waveform kind of generated by these speedboats on the surface of the lake. It kind of spirals out. And their system loses energy due to the waves they're making.
Mm-hmm.
So Newtonian gravity, two objects could orbit each other forever. Like, you could take two stars and have them orbiting each other, and they would stay in orbit from the beginning of the universe to the end of the universe without anything changing.
Right. But Newton was an idiot.
Yes, Newton was a jerk.
What? He was a jerk, but not an idiot.
Oh, okay. Yeah, good correction. So when you add in Einstein, who said that there was a maximum speed at which information could travel through the universe, what it meant was, as these objects were spiraling around each other, the gravitational waves that they made in doing so would carry energy away from the system. And so these stars would slowly lose energy as they spiraled around each other, and they would get closer and closer together.
So you can see this in a kind of conservation of energy argument, because if you have this squishing and squeezing, you could use that to do some kind of work. You could get energy from it. That energy
Put a
has
spring
to be
on
coming
there or
from
something.
somewhere. Yeah, you
Right.
could be putting a spring on there, or I don't know, some sliding rings on a stick that do something.
So could this energy be harnessed to propel you as if like you had a surfboard and maybe it's silver and then you could
Unfortunately, it's much
ride that wave through space-time?
Yeah, to let people know that Galactus is coming.
Unfortunately, it's much weaker than the power cosmic, which, is essentially infinite. Well, the distances we're talking about to these objects are so far away that the amount of sort of power incident on something the size of, say, a surfboard is infinitesimal.
Oh, boo.
You need to have a black hole chasing it.
Yeah, that would work.
So
yeah.
how far away are two pulsars from each other?
So that's the whole point, is they start off quite far away, but as they lose energy from the system, the energy is carried away, and that causes them to come closer together. So they're converting some of their binding energy as being lost to the gravitational waves. So they'll start out quite far apart, sort of the Earth-Sun distance, or it's sort of a standard binary star distance. And then
Right now, the Hulse-Taylor pulsar, the two neutron stars, are only about a solar radii apart. So they've spiraled.
Okay. That's much
They're
closer
really
than
close.
I thought. I thought
Yeah.
it would be like a light year away from each other or something.
No. And you have to recall also that a neutron star is something that's typically a bit more massive than the sun, but it is collapsed down to a ball of basically a nuclear type matter.
It's about 10 kilometers in
10
radii.
kilometers in radius. So that's the size of a small town or a city,
Wow.
a small city. So it's this just ridiculous compression of matter. And that's why these objects, they're compact enough and they're moving at sort of a substantial fraction of the speed of light by the time they get that close. And that's how they can actually churn up space-time enough to create these sort of observable signatures in their dynamics of their orbit, and then potentially something that we can measure directly on Earth.
So you need something
Right.
pretty powerful in order to be able to have even like a tiny, tiny signal that we're able to measure from this far away.
Almost anything accelerating. So if you wave your hands around, you'll be generating gravitational waves. But unless we're talking about black holes or neutron stars or things that are very dense, they won't generate enough of a signal for us to be able to measure it.
So Lovecraft, the author that we cover in our show, was a real science nerd, and he would take different exploration things that were going on in the science world and kind of twist them around into horror stories. Like At the Mountains of Madness is all about polar exploration. And we discovered a story called Out of the Aeons where he talked about all time happening simultaneously, and he was interested in quantum theory and that kind of stuff. So how would gravitational waves, how could they be twisted into a horrific thing? I mean, is there anything that could detrimentally happen? Is there anything horrible associated with this, or does it provide us evidence of something that would blow our minds?
Well, the ripples in the fabric of space-time, the reality itself is warping around you. And that can get kind of crazy when you think about it. There's nothing there but the space between 2 points. There's no stuff there. It's just that there's some change, some deformation that's traveling through nothing, and we can still experience it.
Yeah, it's not like there is an actual surface of a pond that's waving. What's actually waving and oscillating is the definition of distance. So it's like the definition of a meter has been modified by micrometers and is traveling through space. It goes and twists your definition of what a meter is for half a second.
Well, some science fiction writers talk about like gravitational wave guns or gravy guns, where just like you can take electromagnetic waves and make it a laser. Like maybe in the future you could take gravitational waves and make some sort of focused gravitational wave engine of destruction. But that seems a little hard to imagine given the amount of energy and mass that you need to be able to manipulate in order to do that.
Ooh, there's another creepy thing though. There's nothing that can stop them.
Oh no!
It's also very hard to hit anything with them, right? Like
they're very weak, but they'll just keep passing through almost everything in the universe. They'll just shift it around, but continue moving without any. You can't screen gravity. Like if you have some electromagnetic thing, you can put up this field of positive electric charges that will sort of absorb things, but you really can't do that with gravity.
But isn't gravity the weakest of the forces?
Yes. It comes from the fact that you don't have negative gravitational charge. So the fact that you have negative and positive electromagnetic charge lets you screen things out. And so a large electric field, say, can be canceled out by, placing a large part of negative charge near you, for instance.
Well, it's like how we do feel the gravity of the Earth as a pretty strong presence in our life, even though the thin layer of atoms of whatever we're sitting or standing on, there's some electromagnetic repulsion between those two layers of contact atoms supporting us against the pull of the entire Earth combined. But the problem is that on big scales, all those charges kind of average out, and gravity only adds together more and more.
Yeah, most things in the universe are by and large electrically neutral.
Right. So does our sun give off gravitational waves?
It needs to have a motion that is asymmetric in a particular way.
Like a dumbbell rotating or something. So there are modes of the sun that do look like this, but the amount of gravitational waves they give off, the sort of energy that the sun loses to gravitational waves is tiny compared to the energy that's sort of put into heating and dissipation within the sun itself.
Right. Now, what about a supernova? Would that generate?
A supernova can produce gravitational waves if there are these asymmetries about it. So if it's not purely axisymmetric.
If it explodes in an unsymmetrical way, then it would produce these gravitational waves.
Exactly.
Yes.
And actually, if one goes off in our galaxy or in a nearby galaxy, the Betelgeuse, but not for a few years because we're still building them. We're building detectors on Earth right now to try and measure these things directly.
So Betelgeuse, the star in Orion, is on the verge of going supernova. So if we build a detector in time, we should be able to measure all sorts of fantastic things from Betelgeuse when it explodes, because it's very large.
That will tell us how the mass in the center of the explosion moves, which we can't see from the light, which is only emitted from the outer edges. So if we could measure a gravitational wave signal, that tells us about what's happening in the depths of the explosion.
But it's likely that only a small fraction of the energy of a supernova will go into gravitational waves. So a supernova would have to be pretty close in order for us to be able to detect that gravitational wave signal.
Well, how would you observe how would you build an observatory? What device would you measure these with?
That's an excellent
question.
So right now, we've built large, what are called interferometers. They're basically two arms of laser light that, so remember lasers are light.
For Pink Floyd shows, yes.
Right, exactly. That's all in phase. So it's one particular wavelength. And you can think of it traveling as all in phase. And what you do is you have these lasers bounce back and forth along two cavities that are perpendicular. And if one of the cavities is stretched out a little ways compared to the other one. So if you imagine your gravitational wave coming down and making one cavity longer and the other one shorter, then that'll change the phase between the two different arms of light. And then an interferometer is something that measures that phase change very precisely.
Let's back the track up. Okay, so there's a tool called an interferometer that they use in physics. And in this tool, it splits a light beam into two pieces. It has two different arms, and each piece goes down an arm, and then after it bounces down this length, it comes back, it gets recombined, and when it does, it creates an interference pattern based on how long the arms are.
So if the laser is gone, if both beams of light have gone exactly the same distance, they'll still be in phase, so their signals add up. But if they have gone slightly different distances, then they can be out of phase, and so then the signal is slightly less.
If they go half a wavelength, if there's a half a wavelength of light difference between the two arms, that will put them out of phase when they add together again, when the waves combine, and they'll cancel out.
So what you do in these interferometers is once you look at the interference pattern, and if the length of either arm changes by a little bit, the pattern of interference will change. And so what they're looking at is they've got these very long, for gravitational wave detectors, is they've got these very long interferometer arms, and
4 kilometers long.
4 kilometers long. And once the photons recombine, their interference pattern will change slightly if some distance in the two arms has changed. And so a gravitational wave will come in with its different definition for what a length is, and it will kind of make one arm just a little bit smaller than the other arm for a quarter of a second. And so the result is that this interference pattern, when the photons combine, will be different depending on what kind of gravitational wave passes through.
So an interferometer is basically a tool to measure very, very small changes in distance. And Jocelyn, what's the size of distance change that LIGO can measure? Like something smaller than a proton, right?
It's less than 1,000th the diameter of a proton.
There you go.
10 to the minus 18 meters.
So we were saying earlier that if you were in space and you had one of these gravitational waves move through you, first your arms would get compressed a little bit and your torso and head would get stretched a little bit, and then your head and torso would get squished and your arms would get stretched. Gravitational waves are so subtle that they only do so at even if your arms were kilometers and kilometers long, they would only shrink by a distance of less than a proton, a very small distance.
If we're so this is for something that's in the galaxy, several megaparsecs away from us. Detecting at Earth, it moves, say, the distance of a proton.
Wow.
And so the crazy thing is, we've built these. We're measuring this kind of distance difference right now.
So since it has such a minor effect on things, what relevance does it have?
Well, at the beginning, didn't you say something about measuring the waves would allow you to see things in deep or black holes, or be able to detect?
That's right.
Supernovas
so we can,
or something.
Remember that because gravity doesn't get screened, we can actually use gravitational. If we can measure gravitational waves, we can use these to probe what's going on in regions of space we just can't see,
or in regions of space that light isn't being emitted from. So if two black holes collide, they'll emit a lot of gravitational waves, which we'll be able to detect.
I see.
So there's all sorts of things that we can't see. It's like astronomy lets us see things. Gravitational wave detection will let us hear what's going on in the universe.
Yeah. So gravitational waves are essentially an entirely new window into the universe.
Like in Predator, how he would switch his viewer to be like ultraviolet or infrared. If he switched it over to gravitational waves, he could see black holes colliding with one another.
Right. Or like a dumbbell rotating or something.
And
that's awesome. Yeah.
So we can see Arnold working out and then, shoot him from there.
We can actually possibly see some of the background noise from the very beginnings of the universe, even before the cosmic microwave background radiation, which is sort of the last scattering surface of electromagnetic stuff. Because gravitational waves go right through things that screen electromagnetic radiation, we can look further back in time towards the beginning of the universe if there's some sort of background mess of ripples.
It's called a primordial gravitational wave background.
The stochastic background. Yeah, okay, so back this truck up. Okay, so you guys know about the Big Bang, right?
Yes.
There's a theory of the Big Bang. And the problem with our universe is that we can't see the Big Bang. There's a curtain in time. And what happened was very early in the universe, there was a time before atoms existed. And so there were just charged particles flying around. And then sometime in the very recent past, the universe had cooled down enough for charged electrons to start sticking to charged protons. And then
it's not that recent.
It's recent enough. Anyway, so the deal is that light can't propagate until the universe is kind of neutrally charged, until these atoms are made. And so the light we see in the universe now can only go back so far in the history of the universe. And so there's a curtain past which we can't see into the Big Bang. So there's a time when we can definitely observe it. The photons that were generated then are called the cosmic microwave background, or cosmic microwave background radiation. But the deal is that we can't see using electromagnetic waves past that time. And so with gravitational wave detectors, we might be able to see what happened before that curtain, behind that curtain. And so it would give us a window into even earlier in the universe. And crazier things might have happened.
Now, the gravitational wave detectors we've been talking about so far, which are these kilometer-long interferometers, they won't be able to see that background. But there are
unless you have some particularly weird stuff happening. Like there's some cosmological models, like cosmic string backgrounds and stuff like that that would give some sort of signal.
Yeah, there's no telling what we'd be able to hear once we turn on these fantastic gravitational wave ears.
There's a history in astronomy when we discover a new way to see things. Like, for example, when we learned to look at the sky in radio waves, that's when pulsars, which have basically sort of been these fundamental assumptions of what we've talked about today, those were only discovered when we started being able to use radio, which is just a new frequency of light. So when we can actually have a different kind of sense altogether, the really exciting thing is the crazy stuff we don't even know we're going to be able to see.
Well, I mean, what do people predict or anticipate would be the odd things that you might learn if we have detection of gravitational waves? I mean, what are the crazy possibilities?
All right, so there's this one crazy possibility called a cosmic string, and the idea is that it's just kind of an infinitely long one-dimensional object. It's just kind of a string that's infinitely long floating out there.
So you could think of it as like when you have a flaw in a crystal, it can show up as like a one-dimensional dislocation. It can be like essentially a crack in the crystal. Right. This would be basically like a crack in space-time, just kind of like in Doctor Who.
Okay.
As they whip about, sometimes they make gravitational waves.
So if the two strings cross, they can sort of switch partners, like the intersection will split off in a different way, and then what's left are these sort of cusps from where they all touched, and when those evolve, the cusps will emit a burst of radiation in gravitational waves.
So you don't want to cross the streams.
Ah.
So that's one of the potential objects we might see.
Oh, that's one of the more out there possibilities.
And we'll be able.
Some sort of string theory ideas led to considering maybe giant string theory strings as well, which is a different thing, but has a similar kind of signal. Some of the theories have been ruled out actually already because they predict crazy things.
So the gravitational waves will be how we can hear the servitors of Azathoth piping madly at the center of the universe.
That's right. There might be terrible monsters out there that we can't see, but suddenly we'll be able to hear.
Ooh. Do you want to hear what two neutron stars sound like when they merge together?
Yeah.
Okay, let me get... It's been a while, so... That's what the gravitational wave sounds
they
like.
Chirp.
So they as
it's almost like a slide whistle.
As they spiral inwards, or their orbital frequency gets higher and higher and higher, and that's why it sort of ramps up to a chirp.
Yeah, and the kind of the volume of the gravitational wave, the amount of energy they're putting into gravitational waves increases dramatically as this happens.
Because they're closer together, so they're churning space-time around more and more, and that drives them together faster, which, sort of this inevitable collision that becomes more and more dramatic until either the two neutron stars smash together or the two black holes form a single black hole in a sort of weird, bizarre horizon dance.
So if your monster has a vocal cord made of two black holes orbiting each other, then it could definitely be singing out in this sort of etheric, song.
They can get there. There's the so that's sort of stellar mass object. That's kind of the thing that we'd see with our Earth-based detectors. There's other types of detectors, doing giant space laser detectors, or using the signals from pulsars around the Earth as the arm ends of sort of a giant galactic scale gravitational wave detector based on just what we can observe out there.
Yeah, let's go through one by one a variety of the fun detectors out there.
The interferometers that we have on Earth can basically see things can be at around 100, a couple hundred hertz or so.
It's human audio frequencies.
Right.
You can
whereas
just pipe the signal into an audio file and listen to it. There's LIGO, and there's one in Italy called Virgo. There's a little test one in Germany called Geo, and then there's a cryogenic detector being built under the Kamiokande mine in Japan.
Cryogenic?
Yeah.
It's just to cool the electrical equipment to make it have less noise.
So
Is that what
at
they're
low
keeping Walt Disney's head down there?
So yeah, we cool things to cryogenic temperatures, and then we fire lasers at them. It makes total sense.
There's also a possible one occurring in India, right, called Indigo, that may or may not occur.
And all of these detectors are kind of the same construction. They're all very long interferometers, several kilometers long, and they shoot lasers down them. Just
depending on the frequency of the gravitational wave you're trying to measure, you have a whole array of noise sources that you decide which ones you want to focus on. So if you want to be more low frequency sensitive, you're worried about seismic background. You want to have everything suspended by complicated suspension systems to damp out any shifts of the Earth. And
or trucks driving by.
Or airplanes, or tumbleweeds.
So any vibration in the system is going to cause the mirrors to get slightly closer to the lasers and make the interferometer pattern change.
So this is one reason there's a bunch of detectors, because no one's going to believe a signal unless... So this is how you tell whether you're really seeing something from space. If all the detectors see it at once, even though they're more than light transit time away from each other. That means it has to be coming from off Earth and just hitting them all at the same time.
Yeah, so it's a coincident detection from several of these detectors is what you typically need to say, hey, look, we saw this gravitational wave signal. So aside from the ones that are based on Earth that we are currently building and have built, there was a gravitational wave detector that we were going to put in space. It has since been canceled, but the Europeans may be taking it up, and it was called LISA, and may now be called ELISA.
Okay, so LISA is an acronym They're all acronyms, all these different names.
Wait, NASA was going to put this in space?
NASA was
going to.
It was a joint NASA and ESA, the European Space Mission, but
Why was it
NASA
canceled?
NASA couldn't commit the funds, and
Right.
so the Europeans are going to go it alone.
There's no money. The U.S. has run out
Because Americans don't love science anymore.
Yeah, that's sad.
anyhow, so LISA stands for
true.
So LISA stands for Laser Interferometer Space Antenna.
And it consists of 3 basically robots that float in space and shoot lasers at one another. They trail behind the Earth as it goes around the sun, and the separation between the robots is about 10 times the separation of the Earth and the Moon. And they shoot high-powered lasers at one another and measure their change in distance as gravitational waves pass by.
So there are 3 robots in a triangle. There are supposed to be, this is the plan, 3 robots in a triangle shooting lasers at one another.
Nuclear-powered space lasers.
Nuclear-powered space lasers at a distance 10 times the distance between the Earth and the Moon, somewhere in orbit around the Sun, and the distance between them is each individual robot is so large that it will be very accurate for gravitational wave detection.
Yeah.
So this kind of thing would be sensitive to lower frequencies. Lower frequencies are coming from bigger objects that move more ponderously. The massive black holes in the centers of galaxies.
So things that are millions of times the size of the sun merging together when galaxies come together and merge.
So they're not orbiting around each other at, 100 times a second. They're orbiting each other at several times a day or
once every few thousand seconds.
Yeah.
And then, so the lowest, very, very lowest frequency way we have of measuring gravitational waves is what's called a pulsar timing array. And remember we told you how pulsars can act as clock?
Yep.
Well, if you have a whole set of pulsars that we've, been tracking somewhere in the galaxy, we can stare at those pulsars and see how their timing pulses shift. And as a gravitational wave passes by us, we can see the pulsars sort of shift in a correlated way. And from that, we may be able to measure extremely low frequency gravitational waves. Something on the one orbit or one cycle every 10 to the 9 seconds. Every gigasecond.
Every year or few years or 10 years, depending on how long you observe these. So this would be like the biggest black holes merging together. And
if you're going to see the gravitational waves from the beginning of the universe, from before the cosmic microwave background, it's likely that you would see it in this extremely low frequency.
All right, then.
So thank you, Jocelyn and Dave. You have pleased me. Your efforts have borne fruit, and that fruit is sweet. Here's some fruit. Pomegranates for Jocelyn and Dave. Pomegranates from hell.
woo!
Yes. All right.
Hell pomegranates.
You're damned now, Dave. All right. So I'd like to thank my guests.
Damn good pomegranates.
I'd like to thank my guests, Chad Fifer and Chris Lackey. Thank you guys.
Thank you for having us.
It was really fun. You guys asked fantastic questions. Everybody's very impressed.
And we're very, I feel like I'm a whole lot smarter now.
That's good.
Hooray!
Yay.
So yeah, everybody please listen to the HP Lovecraft Literary Podcast. It's lots of fun. All right, so let's close. You can email us at barn, B-A-R-N, at titaniumphysics.com, or you can follow us at Twitter at titaniumphysics. You can visit our website at www.titaniumphysics.com, or look for us on Facebook. If you've got a question that you'd like my titanium physicist to address, email your questions to tiphyter at titaniumphysics.com. That's typhyter at titaniumphysics.com. If you're a physicist and would like to become one of my titanium physicists, email physics at titaniumphysics.com. We're always recruiting. The Titanium Physicists Podcast is a member of Brachial Media. If you've enjoyed the show, you might also enjoy Science Sort of or the weekly Wienersmith. Check them out. The intro music is by Ted Leo and the Pharmacists, and the end music is by John Vanderslice. Good day, my friends, and remember to keep science in your hearts.
Angela, don't be mad. There's something I gotta tell you, dear, before you come back here. I lost your bunny. I let him out of the cage. He was eating spring mix on the carpet, jump through a window out into the haze.